right, good afternoon, everyone. Thank you, Jen. So I'm here to give you an update on our LionGlass project, building a sustainable future for architectural glazing. And thanks so much to the Cocoziello Institute for all of your generous seed grant support. The problem that we are trying to address is the carbon footprint of the glass industry. I come from working in the glass industry. I worked at Corning for 18 years. We made glasses for cell phones, for displays. Despite all of that success, the vast majority, over 90% of the glass being manufactured today, is still the old-fashioned soda-lime silicate glass. This is what is on every window of every building. It's what is in your windshields of your cars, and it has not changed in a very long time. It is responsible for about 95 to 120 million tons of CO2 produced annually. The glass industry itself had kind of put itself into a catch-22 situation because the companies that could afford to invest in the type of game-changing research that is needed to make a step change away from soda lime were not interested in commodity glass markets, whereas the commodity glass industry simply didn't have the profit margin to be able to do that. So we found ourselves in a unique situation here at Penn State with my industrial glass background, a bunch of students who are passionate not only about learning about glass, but about making a positive difference and having these wonderful opportunities for seed funding, such as from Cocoziello. And so we decided to take this problem on. Now, the reason that soda lime is called soda lime glass is that two of the main ingredients are soda ash and limestone. These are both carbonates, sodium carbonate, calcium carbonate, and when they melt, the carbonates decompose into oxides, and they release CO2 in the process. So that is about 20 to 30% of the carbon footprint of the glass industry. The remaining 70 to 80% is due to the high temperatures from melting of the glass. This requires temperatures of about 1450 to 1500 degrees Celsius, so very high temperatures. What we did with LionGlass is to invent a new family of glass chemistry that completely changes the chemistry of the glass to lower the melting temperature by about 400 degrees C, while also completely eliminating the use of carbonate batch materials. So the melting temperature is brought down to 1100 or even a little bit below that. We also found, surprisingly, that LionGlass has about 10 times the damage resistance compared to soda lime silicate glass, which means it takes a lot more stress in order for cracks to pop in. And this may also be a pathway toward lightweighting of glass products, since better mechanical properties mean that you can go to thinner walled products. The table down here in the bottom shows the emissions, milligrams of CO2 emitted for every gram of glass produced. And you can see that for soda lime silicate, this is about 193 milligrams per gram of glass, whereas with LionGlass, just from the batch to melt conversion process, that's basically atmospheric CO2. So the global glass industry is divided into many markets. Obviously, these glasses are used for the glasses that you drink out of at dinner, glass bottles for beverages, for food, but the majority of this market is in architecture. So about 65% is in the architectural space. And if you look around, it's not surprising why that is the case when you look at the size of windows in modern buildings. So we've secured intellectual property. We have 4 or 5 patent applications out there now. We were able to get some very positive attention from the international press here and BBC. We've had 2 successful trials in Italy already. The first one was in Murano, which is, of course, outside of Venice. This has a history of glassmaking going back over 1,000 years. These are photos from that first trial in Murano. We've had a second trial in Florence, and we were able to produce glass cups manually and using an automated process. Here is our LionGlass team. So I am working together with Dr. Julian Wang in architectural engineering. He knows so much about the energy efficiency of buildings and window designs, and so we've made a great team together. Nick Clark is leading the day-to-day LionGlass efforts. He's an assistant research professor in my group, working with Mina Mehmet, who is directly funded by the seed grant, Aleph, and Elizabeth. We have 4 companies that we're working with now. Bormioli was the first. They are interested in the space of using LionGlass for cosmetics packaging. Then we formed a contract with Veralia. They are using, or would like to use LionGlass for high-end spirits packaging. And the one that I'm most excited about, the one that was made possible by Cocoziello, is this top one here, Vitro. So if anyone remembers, one of the big companies in Pittsburgh is PPG, right? This stands for Pittsburgh Plate Glass. Now it doesn't stand for that anymore, it just stands for PPG. But they sold off their flat glass business to Vitro, which is a Mexican-based company. Their US headquarters is still in Pittsburgh. And so they are funding a project with us now and for the next 3 years to do LionGlass for architectural applications. And the process, the key process that needs to be done is to ensure that what's called the float compatibility of LionGlass. The way architectural glass is made is that it's floated on top of a bath of molten tin. So you've got molten tin metal. The molten glass is lower density and it floats on top, and then it's pulled horizontally and gradually cooled. That's how you get these really large windows with such pristine surface quality, because one side only touches liquid tin, the other side only touches the air. So we are working with them right now. Everything is looking positive. It looks really good, actually, with respect to tin compatibility, and we're hoping by the end of this project to actually be able to have some prototype samples made via the float process. The fourth company that's listed here is RedWave Technologies. Another big issue is recycling. RedWave is an Austria-based company that makes the equipment for sorting basically recycled things. And so we're working with them to upgrade their equipment. It's an XRF, so X-ray fluorescence technique for sorting different types of materials. And so we're working with them so they can update their software to identify LionGlass. So the big question for LionGlass in the architectural space is, can we produce flat sheets of LionGlass? We did this manually in the lab. There's a lot of trial and error involved. We had to get rid of some cracking problems, some bubble problems, and eventually you can see the progress here that we were able to do it in the lab. This shows some of the movies here showing the glasses that were produced. Next, can we coat LionGlass to meet industrial glazing standards? This just shows some typical U factors for different parts of a home. And what you can see is that the biggest energy loss here for buildings occurs through the windows. This is significantly worse than walls, floors, and the roof, of course. And so there's a need for energy efficient glazing technologies, and we've been working closely with Julian to make this happen. So the emissivity of uncoated soda lime silicate versus uncoated LionGlass, they came out to be identical, so we were really happy with that. And then the next question is, what about coating? The low E coated soda lime silicate brings the emissivity down significantly. We don't have the complete professional setup to do that here, but we were looking at applying some low E coating manually. You can see on the lower right, this shows uncoated LionGlass versus coated LionGlass. You can see a little bit of the coating there, and you can see in the table that the LionGlass with low E coating has an emissivity of 0.14, which is within the range of reported for soda lime. And so we were very happy with that progress there as well. And it is also showing a really good visibility, really good transmission across the visible spectrum. One of the things that I want to note, especially in the architectural space, is that LionGlass does not have the greenish tint like standard soda lime glass has. Like if you look through a window just sort of through the thickness, you don't really notice it. But if you turn it and look through the width, you'll notice that window glass is not actually clear. It's green. And it's green because of small amounts of iron contamination. And if you want to pay extra to get clearer glass that isn't green, you know, the companies will charge you extra for that. And with LionGlass, you get that automatically because it takes a lot more iron in order to produce coloration. And so the final thing that we're working on with Julian is to actually make a prototype IGU. We have some ideas about how to improve the design of the IGU itself as well. And so we are working on that. Another space that we're working in is like LionGlass for vacuum insulated glazing, because one of the next generations of glazing technologies is going to be, instead of having a noble gas in between the two panes, you'd actually pull a vacuum, and that creates mechanical stresses, which means that the glass needs to be able to withstand fatigue behavior over the lifetime of the building. So we've been working on that. We've also been characterizing all the properties like haze, to understand if LionGlass gives the appropriate performance for architectural applications. And if I go forward here, everything was looking good so far in terms of its optical transmission, the haze behavior, the U factor. And so bottom line is things are looking good. We haven't encountered any showstoppers yet. The COCO's funding was just what we needed to get our foothold in the architectural space. This has directly led to a patent application. It has directly led to a 3-year contract with a major North American producer based here in Pennsylvania. And so this is great because it's also consistent with our land grant mission. So with that, I want to thank you. And I think I used up probably more than my time. Thanks, everyone. Okay. Any questions?
I have one. Vizio or Viso, do they manufacture in the United States?
Vitro manufactures in the U.S. Yes, they manufacture in Carlisle. They've got a float glass factory in Carlisle, and they manufacture just north of Pittsburgh also.
I was just thinking, if they manufactured stateside, but they're manufacturing in Pittsburgh,
Yeah.
what a
Yeah.
great opportunity to
Yeah.
bring research teams to the manufacturing floor to really understand
Absolutely.
all the stuff that goes into what they're inventing, what
Yeah,
they're working
yeah.
on, studying. It'd be great.
Yeah, and another cool thing, the PhD student who's leading this project, he actually did his bachelor's and his master's degree here at Penn State with Carlo Pantano. You know Carlo, right? And I was actually part of the team that hired him at Corning. I left Corning to come here. He left Corning to go to Vitro, and now Vitro's sending him back here to get his PhD working on LionGlass.
That's
So,
incredible.
yeah.
That's great.
Yes.
Have you experimented with different thicknesses of glass?
So we are making different thicknesses in the lab. We haven't done any systematic studies yet of different thicknesses in terms of IGU design. Not yet. Yes.
Is there structural integrity in this glass?
So I would hesitate to promise anything beyond what current glass offers in Windows. Because even though it does have improved damage resistance, it's still a brittle material. I mean, we are thinking about, can we use LionGlass as kind of a filler in maybe polycrystalline ceramics or something like that to lower the processing temperatures of ceramic sintering. That's another idea that's kind of on our list to explore.
The follow-up is weight. What is the weight?
The weight is, the density is very similar to standard soda lime. So the weight would be the same if it is the same thickness. All right, thanks everyone.